Hello. The last video, I talked about the astable multi-vibrator using an op-amp. And at some point, I think I went a little bit too fast about something that probably deserved a little bit more explanation, because maybe it's not that obvious, or maybe it's interesting to look into it in more details. Okay, so this was the thing I was trying to explain. You had like a voltage divider, and you had your VCC here, the 9 volts, so that's the battery voltage. Ground here, and here, that was basically the output of the op amp, and it was either going into positive saturation at 9 volt or negative saturation, 0 volt. In actuality, it's not really 9 volt, it's probably 8, and here it's probably 1, but for the purpose of this, let's say it's full VCC, so 9 volt, 0 volt. So, and I'm interested in this voltage here, the VA, this voltage at this point. So, if you have positive saturation, I said that VA is equal to 4.5 volts plus epsilon, epsilon being relatively small. So maybe, I don't know, 0.2 or 0.3 volts. And if you go to negative saturation, VA is going to be equal to 4.5 volt minus epsilon volt. So I kind of stated that without really explaining why. And I think this is a very good way to look into the Thevenin theorem or Thevenin equivalent circuit. So that's what we're going to do today in this video. Okay, so the first thing we need to do is to redraw this thing into something that looks like a linear circuit with resistors and voltage sources. I mean, here it's not super clear because I just say 9 volt, I don't have the connection. So let me redraw, and it's going to be exactly the same. It's exactly the same. So you're going to have your 10K, the R1 here. This is your A. That's the voltage where you want to know the voltage, compute the voltage. And this is R2 here, 10K. So then it goes here to the battery, which is the 9 volt one, the VCC, like this. And then you have this guy here. So that's the R3, 100K. And that's going to a virtual battery. I mean, it's not really a battery, it's just a voltage that we measure, I mean, that we know is supposed to be there. Or it could be a voltage that we measure, that's all we know about it. But it's represented as a battery. So it's either 9 volt. So let's put it as X volt, we don't know. It can vary. So if we go back again, here, that 9 volt, 0 volt is actually the output of the op amp. So it's not really a battery, but we can do as if it was a battery for our own purposes, because clearly if you put an op amp, it's not a linear circuit. But if you know the voltage here, or if you measure it, then you can use the Thevenin theorem to get this guy. Same thing here. Here it's a battery, but you could have measured some voltage and you want to know the voltage here. Okay, so this is the setup. So now we have to do the Thevenin. So we need to compute VThev and RThev. Basically, what happens is that this circuit is going to be equivalent to this circuit. Here is the VThev. It's a voltage source with a plus and a minus. Here you have the RThev, so this is RThev. And here you're gonna have this guy, the R2. Okay, so this is A, this is, let's put it as B. So now you have A here and B there, B here. So this is the equivalent Thevenin circuit, equivalent Thevenin circuit to this. This is the same thing. And once you have that, it's very easy to compute VA or VAB or the current that goes through this thing. I mean, here you can see it as a load. It's like the load resistance, really. So let's compute VTEV and RTEV. Okay, so I have to compute VTEV. So VTEV, how do you compute that? It's VTEV is VAB. VTEV is VAB. So this is this voltage here that we are trying to figure out. So how do you compute that? Oh, yeah. Yeah, so VTEV is equal to VR3. So this voltage here, VR3 plus XV. But what is VR3? VR3 is part of a voltage divider going from here to here, right? Oh yeah, I forgot to say that when you compute VTEV, you have to remove this guy. I need to remove it. I forgot that. Sorry about that. Yes, when you compute VTEV, you have to remove this guy. Because here we have the resistor between A and B, you have to remove it. Because it's considered as the load. So you remove it and then you compute VTEV, which is here. So this is VTEV. This is VTEV. Sorry about that, was not super clear. Okay, so VR3, it is now a voltage divider, okay, from here to here. So VR3 is equal to R3 divided by R1 plus R3 times, it's going to be this voltage here, 9 volts, minus this voltage here, so minus XV. So VTEV is equal to R3 100. R1 plus R3 is 110 times 9 by X. Oh yeah, we know it's volts. So 9 by X. 9 minus X. So this is VTEV. Okay, so if X is equal to 9, so positive saturation, VTEV is equal to, this one is easy, should be easy, because VTEV is what, 0, right? Hold on, let me check, just to be sure. Oh, I knew there was something wrong. Yeah, I forgot the plus XV. Plus XV. Yeah, that was not right. So VTEV equals, so this is 0, X equals 9, so VTEV is equal to 9 volts. If X equals 0 volt, VTEV, let me check on my piece of paper because I did this some time ago. 8.2. So you just plug 0, yeah. And yeah, so yeah, it's a little bit less than 9. Okay, that's correct. Okay, so we have VTEV. And again, to compute VTEV and to compute RTEV as well, you have to remove that resistor because our two measuring points are connected by a resistor, so you have to remove it. Okay, so that's VTEV. Now we have to do RTEV. Okay, so now we need to compute RTEV. What is it? So let me go back to quickly. So this is R1, 10K. This is A. This is R2, 10K. You have your battery here, the 9 volt. And then you have your R3, 100K. Then you have the X volts here. So to compute RTEV, again, you have to remove this guy. And you have to short circuit the voltage sources. So you're like that. And you have to compute the resistance between those 2 points. So RTEV is equal to RAB. And it's equal to those two in parallel, right? So it's equal to R1, R3 divided by R1 plus R3. So it's equal to 10 times 100 divided by 110. And this is equal to 9.1 K ohms. 9.1 K ohms. So that's pretty good. So now that we know VTEV and RTEV, you can do this thing. I think I'm going to do it here. I'm going to put it here. So we have plus, minus. This is RTEV, VTEV, and you have your R2. So this is A, this is B. And you have now your R2 is here. And this is a 10K. And okay, so if X equal 9 volt, VTEV equal 9 volt, and if X equals 0 volt, VTEV is equal to 8.2, and here we have RTEV. And here you have a, what do you have? You have a voltage divider to compute VR2. So VA is equal to VAB is equal to VR2, and VR2 is equal to it's equal to R2 divided by RTEV plus R2. This is voltage divider formula, and it's gonna be VTEV here. So you just plug in the thing, right? R2 is 10K, RTEV is RTEV is 9.1K, and VTEV is either 9 volt or 8.2 volts. So if X equals 9 volt, VA equals 4.7. And if it's 0 volt, VA is equal to 4.3. So here you can get, so this is what I was trying to do, get the VA for X equal 9 volt and X equals 0 volt. So you can get the exact values if you're doing this Thevenin theorem thing. Okay, so that's that. And Thevenin theorem is, as you can see, pretty powerful. But if you don't want to go through all this and you don't care about the exact value, you can kind of guess what those values are supposed to be. It's a bit of a guessing game, but it's close enough. More intuitive, I guess. So let me go back to the original problem. So you have R1 10K. This is your A. R2 10K ground, and here you have your R3 100K, and here you have your either 9 volt or 0 volt or whatever you want, really. If you don't have this connection, if you don't have this branch, if you don't have this branch, you know that this is 4.5 volts, right? If you don't have that branch, it's voltage divider, same values for the resistor, so it takes half. You know it's going to be 4.5, and you know that you're going to have some current going through this. Ohm's law. Huh? So what happened, let's say, when you put 9 volt, you do the 9 volt, and you connect. So you connect. So here you're going to have some, not much, some current going this way. Not much because of the large resistor here. So you're going to have current going this way. It's going to hit A. So here you probably, if you look at this branch, the voltage here is probably pretty small. Pretty small. So obviously it cannot go towards the 9 volt. It's going to go towards the ground. So it's going to go this way. And the current that was in the branch, it cannot go this way because of the 9 volt. So this guy doesn't go this way. Okay, only this guy goes that way. So here, what's going to happen is that this current is going to be added to this one to get you a greater current. So since VR2 is equal to R2 times I R2, and since R2 has increased, VR2, which is equal to VA, VR2 is going to be equal to 4.5 plus something else. Okay, because IR2 is the old current, the one without connecting the branch, plus epsilon. So it's going to be the IR2 prime, the one without the branch connected, plus epsilon I. So some current, or should I say epsilon, yeah, the amp sign or whatever. And because of these guys, you're going to get epsilon here also, because of the Ohm's law. So that's how you can tell that the voltage is going to increase as soon as you connect that branch. Okay, so now if you do 0, put 0 volts here, you connect the branch to here, what happens? What's going to happen is that this current is going to go this way, but less, because some of it is going to go that way. So a piece of the current, of this current, is going to go this way, right? A little piece, because this is a large resistor. So this guy is going to be less than it was. It's going to be less than it was. So here on the 0 volt, so you still have VA equal VR2 is equal to R2 times IR2. And the IR2 is equal to IR2 prime. So the current through the resistor R2 when the branch was not connected. And this time it's minus epsilon, because some of that current is going through that branch. So that's why you get VA is equal to 4.5 volt minus epsilon volts. Okay, I hope it's clear. But if you don't want to bother with this, you can just do the Thevenin theorem, and then you even get the exact values. But this is like when the circuit is simple like that, you can just do it this way, and you can tell that the VA increases by a little bit or decreases by a little bit depending on the value here. Okay, I think I'm going to stop here, and I'll see you around. Bye.